Welcome back to Reactor Heat Transfer. We're going to talk now just a little bit about flow over what we call bluff bodies. Now, bluff bodies are things that are sitting in a flow that are not aerodynamic. Things like spheres or cylinders, trees, people even, can be considered bluff bodies. Now, for engineering work, the long cylinder and the sphere are typically the most important bluff bodies. However, there are a number of other geometries that may be important for specific applications. Now, the thing to remember here is that the flow is much more complex than for flat plates or for streamlined bodies. If you look at the forward edge of this sphere or cylinder, you have a stagnation point where the velocity is 0. And then the flow speed varies around the edge of the object to a maximum here at 90 degrees from the front. So you have pressure gradients based on Bernoulli's equation. That makes it much harder to predict the Nusselt number. It's going to vary depending on position around the edge of the object. And then you may also have boundary layer separation here, where the boundary layer separates from the surface and you have the formation of a turbulent wake in this area. And that's going to change the behavior on the back side of the object and make the analysis even more complex. So boundary layer separation affects the pressure distribution around an object. You can see here you have the theoretical perfect boundary layer behavior for the angle around this cylinder from 0 to the back of the cylinder, 180 degrees, and then it comes back around to the front of the cylinder here. But we don't really need to worry about this part very much. We're just looking from 0 to 180 degrees. So theoretically, the pressure at the back of the cylinder should be the same as the pressure at the front if you have a perfect flow with no boundary layer separation. However, if we look at a case where we have a Reynolds number below what we call the critical Reynolds number, which shows up here for the transition from a laminar boundary layer to a turbulent boundary layer. So in this case, this dashed line here represents our laminar boundary layer case, and you can see that the pressure doesn't change by as much, and you have this large region in the back side of the cylinder where the pressure never recovers, and this creates drag, right? And you can see the difference in behavior once we trip the boundary layer to turbulent, and we can reduce the drag. So this also affects the behavior of the Nusselt number. If we look, we can see that the Nusselt number is going to vary depending on position according to our boundary layer separation. So at low Reynolds numbers, boundary layer separation occurs here, resulting in an increase in heat transfer coefficient in the turbulent wake. And at very high Reynolds numbers, the boundary layer transition moves to the backside of the sphere, and we have the cylinder, and we have a much larger spike in heat transfer coefficient. So if we convert this to an average Nusselt number, we can look at this graph over here, where we've correlated wires of different diameter on a Reynolds number, Prandtl number, Nusselt number graph. And the results are actually quite good. They all fall essentially on the same line. So analytical methods have had only limited success with these kinds of flows because they're so complex, and we typically rely on these empirical methods where we collect a lot of data and then correlate it. So in general, we're going to talk now about some empirical correlations, and correlations with more limited ranges tend to be more accurate over that range. They are, however, less accurate outside of that range. So which correlation you use depends on what the conditions of your problem or your experiment are. Now, the Hilbert correlation is reasonable when the surface temperature and the free steam temperature are fairly similar, so that there's not a large energy transfer. The Zakauskas correlation serves when the surface is much warmer or much cooler than the free stream. Now, there are other more complex and more accurate correlations in the textbook. However, these provide reasonable values over a pretty wide range of conditions if you use the correct values for C and M based on the Reynolds number. Now, it's reasonable to use these two correlations, which are designed for infinite cylinders, if the length to diameter ratio of the cylinder is greater than 4. That's close enough to infinite cylinder that these models are reasonable. And again, remember, empirical correlations require the use of the film temperature unless otherwise specified for a particular correlation. We can also look at spheres. Now, the boundary layer effects on a sphere are very similar to those on a cylinder. So for McAdams, where you have heat transfer in a gas, you can use the correlation given here for a pretty wide range of Reynolds numbers, and it's actually almost independent of Prandtl number. If you have liquids or gases, you want to use something closer to the Whittaker equation, where there's some Prandtl number dependence, and you also see there's a relationship here between the free stream value and the surface value that needs to be accounted for in the viscosity ratio. You can also use these kinds of correlations for a pretty wide range of other Bluff objects. This presents a pretty limited selection. There's a lot of other tables like this that can be found in textbooks and online for a pretty wide variety of Bluff bodies, but they all pretty much have the same formula. Some constant times the Reynolds number to a power times Prandtl number to the 1/3.